Hello. Have you ever found it difficult to find domains of functions? Or is there a certain type of functions that you find it tricky to find their domains? Well, in today's lesson, we're going to try to find different domains for different types of functions and how we do so by explaining the concept of domain itself. If we understand the concept of domains, then we can get domains for any type of functions that faces us. But first, Assalamu alaikum, welcome to my channel, FM Maths, providing mathematics and physics tutorials for secondary level and beyond. Make sure to subscribe so you can easily find all lessons and to write down any requests that you may have in comments so they can be added in future videos. Now going back to our topic. In order to understand domain, let us depict functions as machines. If you have a machine, you know that any machine you have to provide raw material, so you can get a product. And that works as a function actually, because if you insert in a raw material plastic, you'll get a product that is made of plastic. For example, a plastic toy. If you insert in your raw material inlet, let's say leather, you might get something like a leather bag. And so on and so on. So a machine would take raw material, then process it inside the machine. It gets processed so you can get a product. But this product is going to be depending on the type of raw material that you use. And that's exactly how functions work. If you have a function, let's say that the function is f of x equals x squared, then depending on the raw material you put, the raw material would be x. You put values for x, different values for x. So if you put x equals 2, that's a value for x. It gets inside the machine or the function, gets processed, x squared, so 2 squared equals 4. And you get the product, which is y equals 4. If you put in this machine x equals 3, then it's going to get inside the machine or inside the function, gets processed again. 3 squared equals 9, and so you get y equals 9. And this is how it works. You put values, different values for x, they get processed by the function, and then you will get a value for y. And so we can use this to understand the term domain. Now, let us say that for any machine, it cannot just take anything. For example, if I put plastic, I get a plastic bag. If I put leather, I get a plastic toy. If I put leather, I get a leather bag, and so on. But can I use just any kind of raw material that I can imagine and get a product out of it? Well, that doesn't work for most of machines, actually. For every machine, there are certain types of raw materials that you can put that they will give you a product. For example, you might say, okay, I want to use oxygen in this machine. And you put oxygen inside and nothing comes out. Why? Simply because this machine does not process oxygen. You cannot get something out of that. But you can use plastic, you can use leather, you can use even metal. But you cannot use paper, for example. And very much that is actually domain. All the raw materials that I can use in this machine that will actually give me a product, it's in the domain of this machine. If I put a certain raw material in this machine, but I could not get a result or I could not get a product, then this raw material is not in the domain of this machine. And that goes for functions. If I use a different function, let's say that f of x equals 1 over x, there are certain values of x that I can put in this function to get a result. If I put x equals 1, then I'm going to get y equals 1 over 1, which is 1. If I put x equals 2, then I will get 1 over 2. But if I put x equals 0, now 0 gets inside the machine or inside the function, and the function is going to try to process it 1 over 0 because it's 1 over x. But then 1 over 0 cannot be done because we cannot divide by 0. And so we will not get a product. So 0 is not in the domain of this function, while 1, 2, 3, 4, 5, any other number is actually in the domain of this function. So we can say, or we can identify domain as all possible values of x that would give a real value in y, and it has to be a real value because there are in some functions you can actually use some values for x and you will not get a real value, you'll get an imaginary value. But we're focusing here on getting an actual real value. What do I mean by a real value? I mean that the value in y has to belong to the group of real numbers. It has to be a real number. And there is actually a machine that does that. If you use a calculator and you put in a calculator 1 over x and then try to put x as 0 in this calculator, it will simply tell you that it cannot do that. Most calculators will say syntax error, and this literally means that this function cannot be done with this value, or you cannot divide by 0 or anything. So pretty much that is the simple explanation of domain. But through this simple explanation, we can find it easy now to get all kinds of domains to different functions. Let us divide functions into 3 groups to find their domains. And the first group would be the polynomial function. What are polynomial functions? Polynomial functions go like this. If you have y equals x to the power of 4 plus 3x to the power of 3 plus x to the power of 2 plus x plus, let's say, 7, this is a polynomial function. A polynomial function has many terms that go in a linear way. Those are polynomial functions. And polynomial functions are the ones that are easiest to find domains for, because the domain for any polynomial function is just R. The domain for any polynomial function is just going to be the group of real numbers. That means all numbers from negative infinity to positive infinity are in the domain of this function. Or also we can just say that any number that you can imagine is going to be in the domain of this function. Any number that you can imagine, you can put it as a value for x and you will get a value in y. So whenever you find yourself dealing with a polynomial function, the domain is straight R. And so we can move on to another type of function, which is the rational function. Now, when we're looking at a rational function, we find it to have a numerator and a denominator. So we can say like f of x equals, let's say x divided by x minus 2. So here now I have a denominator. And once I have a denominator, then the domain becomes less. Because when I have a denominator, I know that there is a case for this fraction. When that case happens, I cannot solve this fraction. And this case, when the denominator equals 0. You cannot divide by 0. And so this function can work for all values of x except when a value of x makes the denominator equaling 0. And that's from the definition of domains. If there is a value that I use in this function that will make the denominator equaling 0, then this value will not give me a value in y, and so it's not going to be in the domain for this function. So if we find ourselves dealing with a rational function that is a function that has a denominator, that means I'm going to be looking for the value that makes this denominator equaling 0. So I can simply just say that x minus 2, which is the denominator, equals 0. And then solve for x, adding 2 to both sides, x will equal 2. So if I use 2 on this function, I'm going to get 0 in the denominator. So the domain of this function is going to be the group of real numbers, all of it, except for one value, which is 2. Any other value that I use for this function is good, except for this one value. And we can always write domains in two different ways. We can write domains in this way, which is using groups or sets, and we can use intervals. We can write it using intervals. Now we know that an interval, we put two numbers, and all the values between those two numbers are acceptable values. So the domain of this function can be written as all the numbers between negative infinity and 2, and all the numbers between 2 and positive infinity. All the numbers between negative infinity and 2, and then all the numbers between 2 and positive infinity. This is me saying that everything goes from negative infinity, but 2 here is not with us. Yes, I wrote it in the interval, but this interval here is open. And when the interval is open, the number itself that is written inside the interval is not counted. If the interval is closed, then 2 is counted, but I don't want to, so I'm going to put it in an open interval. So from here we can go back to polynomial functions. If I have a polynomial function like this, but in one of its terms it has x as a denominator, then I have to pay attention to this x. Because if the function now has x as a denominator and I say that the domain is R, then I'm mistaken. Because now there is a value of x, which is here, in this case it's 0, that will make this unsolvable, and so I'm not going to get a value in y. If it's x minus 2, then the value becomes 2, because 2 minus 2 equals 0, and so on. So that's it for the rational function. We can have an example. Let us say that I have the function y equals 3 divided by x squared minus 9. Let's make it x minus 3. Okay, x minus 3 divided by x squared minus 9. Now, first of all, this is a rational function. So the numerator is irrelevant here because any value of x in the numerator is okay. But the problem is the denominator. So when we're faced with a rational function, you only just care about the denominator. So I have to look for the value in the denominator that makes it equals 0. So I'm going to say that x squared minus 9 equals 0. Now x squared minus 9 is a difference between two squares. So it's x plus 3 multiplied by x minus 3. And all of that equals 0. Now here I have two numbers or two values. When multiplied by each other, give me 0. If I have a multiplied by b equaling 0, that means either a is 0 or b is 0 or both of them. So I have to look into those options. One of those two values must equal 0. So x plus 3 is the first value. If it equals 0, then x is going to be negative 3. And the second value, x minus 3, if it equals 0, then x is going to equal positive 3. So negative 3 and positive 3 are the two values that if I use on this function, I'm going to get a 0 in the denominator, and so those two values cannot be in my domain. Any other value is okay. So the domain for this function is going to be r minus negative 3 and positive 3. That means all real numbers are okay except for negative 3 and positive 3. Moving on to a different type of functions, and this time we're going to look for a square root function. Now, square root functions, as the name, are functions that have x or that have, it doesn't have to be x because we can have any different variable. So they have the variable of the function itself under the square root. Now here we must pay attention to something. Cube roots are not the same as square roots. So they do not follow the same rules because of what we're going to explain now. So if I have a function, let us say that f of x equals 2x minus 1. So when we're dealing with roots, we need to find all numbers that can be used under the square root that will actually give me a value. And we know that if I have 2 squared, it equals 4. And if I have negative 2 squared, it also equals 4. So if I multiply two numbers by each other, if I multiply any number by itself, I'm always going to get a positive number. There is no way that I'm going to get a negative number. If you say that I multiply negative 2 by positive 2, then yes, I will get negative 4, but negative 2 and positive 2 are not the same number, so I'm not multiplying a number by itself. So in the square root, I should be looking for only positive values. Any value of x that will cause me to get a negative number under the root is not in the domain of my function, because if I end up with a negative number under the root, then I'm not going to have a real answer. And this is the case when we actually going to find an imaginary answer. If I say negative 4 under the root, it can be 2 multiplied by the square of negative 1, and the square of negative 1 is I, which is imaginary. But I'm just looking for real numbers, so that means negative 4 under the root is not part of my domain. So whenever I'm facing with a square root function, I need to make sure that I do not end up with a negative number under the root. Okay, how do I do that? How do I make sure of that? Well, then I need to mathematically say that 2x minus 1 is a positive number. And to mathematically say that, I'm going to say that 2x minus 1 is greater than 0. This is the literal meaning of a positive number, greater than 0. But hold on. What is the square root of 0 itself? Does it have a square root? Yes, 0 does have a square root. The square root of 0 is 0, because if you multiply 0 by itself, you're going to get a 0. So 0 can be in the domain, because I will get a real answer. 0 is a real number. So 2x minus 1 is not greater than 0, it's greater than or equals 0, because 0 is good with us. Okay. Then solve for x. 2x minus 1, 2x is greater than or equal 1. Then divide both sides by 2, and I will end up with x being greater than or equals 1 over 2. So the domain of my function is any number that is greater than or equals 1 over 2. Any number that is greater than or equals 1 over 2 is a part of my domain. Any number that is less than that is not a part of my domain, because I'm going to end up with a negative number under the root. So I can say that the domain here, in the form of groups or in form of sets, is the group where it contains x, so that x is greater than or equals 1 over 2. X is a real number. This is as a set. If I want to write it as an interval, then it's going to be an interval which has 1 over 2 up to positive infinity. All the numbers between 1 over 2 and positive infinity. And the interval is going to be a closed interval. Why a closed interval? Because 1 over 2 here is accepted. It's greater than or equals. If I put it as an open interval, that means 1 over 2 itself is not included, but 1 over 2 is included in my interval. So the domain in an interval way can be written like this. Type. What about a cube root? What about a fourth root? Now, cube roots and fourth roots are different, because you can have a negative number under the cube root. For example, negative 2 to the power of 3 equals negative 2 multiplied by negative 2 multiplied by negative 2, which equals negative 8. So if I have the cube root or the third root of negative 8, there is an answer for that. The third root of negative 8 is negative 2. So if the function is under a third root, I don't have to do this. Okay, what if it's under a fourth root? Okay, let's see. Negative 2 by negative 2 by negative 2 by negative 2 again equals, here I have 4 and here I have 4, and this equals 16. So again, with the fourth root, I cannot have a negative number under the root. So basically, when it comes to roots in general, I only have to make sure that is greater than or equals 0 if it's an even root. Square roots, fourth roots, sixth roots, and so on. But odd roots are okay. Third roots, fifth roots, seventh roots, and so on are okay. I don't have to do this because I can have a negative number under those roots. And this is basically how we find domains for square root functions. Now again, what if I have a polynomial function, but in one of the terms I have x under the root or the variable under the root? Then I have to make sure that x is not a negative number again. I have to make sure that I don't have a negative number under the root again. So the domain will be R, but all the values that will give me a negative number under this root are going to be excluded from this domain. And that's basically all kinds of functions that we can face and be required to find domains for. But sometimes, let's talk about some special cases. What if I have a function now that has different elements of the functions that we mentioned? What if I have a function that looks like this, 3x minus 1 under the square root and divided by x plus 2. Now this is a function that has this element, which is not having a negative number under the root, and it has this element which is not having 0 as a denominator. And so I'm going to have to do the both of things. I have to make sure that x will not give me a negative value under the root. So I'm going to say that 3x minus 1 has to be greater than or equals 0. And so 3x is greater than or equals 1. And so x has to be greater than or equals 1 over 3. Okay then. We look into the other option here. I need to make sure that in the denominator, x plus 2 does not equal 0. So if x plus 2 equals 0, then x equals negative 2. So now I have two conditions. The first condition is x has to be greater than or equals 1 over 3, and the second condition is x is not supposed to be equaling negative 2. And I need to write those two conditions, but luckily those two conditions work with each other because negative 2 is already smaller than 1 over 3. So I can just say that the domain is one over 3 up to infinity. But okay, let's change it. Let's say that here it's 4 x minus 4. No, x minus 4, yes. So x minus 4 equals 0. So x equals 4. 4 is greater than 1 over 3. So all I have to do is just take 4 out of this domain. So instead of this, I will make it 1 over 3 up to 4, and then from 4 to infinity. Again, I put an open interval here because 4 is not a part of my domain. Okay, what if I have the function f of x equals 3x divided by 5x minus 6x minus 2 under the square root. Again, I have two conditions. The first condition is that I don't want a negative number under the root, and I don't want a 0 in the denominator. So 6x minus 2 should be greater than or equals 0, so I do not have a negative number under the root. But if I have 0, then I'm going to get a denominator as 0. So I'm just going to make it 6x minus 2 is just greater than 0. Now 0 is excluded because I don't want 0 here. So it's going to be 6x greater than 2, dividing both sides by 6. X has to be greater than 1 over 3. And so the domain is going to be 1 over 3 to infinity, but 1 over 3 in an open interval, because 1 over 3 itself is not included. X has to be greater than 1 over 3, so 1 over 3 is excluded from our domain. The last case I want to talk about, what if I have f of x equals tan x? Now, from the first look, this looks like a polynomial function. It doesn't have a denominator and there are no square roots, so this looks like a polynomial function, and so I can say that the domain is just R. Correct? No. Actually, tan x is a fraction, because we know that tan x equals sine x divided by cosine x. And now I have a denominator, and I need to find all the values that make this denominator 0. Like, what are the values that will give me 0 in cosine x? Well, cosine x is a periodic function, and it has many zeros in it. The values that will give me 0 for cosine x are the angles 90 and 270 and 450 and so on, and even so on with the other side, from negative to positive. So in this case, I can say that the domain for this function equals all values except for positive or negative 90 degrees, positive or negative 270 degrees, positive or negative 450 degrees, and so on. A best way to write this is write it in radians. So you can write, say, r minus plus or minus pi over 2 plus or minus 3 pi over 2 plus or minus 5 pi over 2, and so on. So here are the values that if I use them in cosine x, I'm going to get a 0 in the denominator, or if I use them in this function, which is tan x, I'm going to get a 0 in the denominator. So those values cannot be part of my domain. Like, what if f of x equals cosine x itself? Now, if it's equals cosine x or sine x, there is no problem. This is just a polynomial function where the domain is just all of r. Because any value for cosine x and sine x are acceptable. But tan x, cotan x, sec and cosec, all of those are fractions. So for those functions, I need to break them into their fraction form and then look for the angles that will make the denominator equals 0. And that will be excluded out of my domain. I hope that this video was educational and enjoyable. And don't forget to subscribe so you can easily find all the videos you need, and to write down any requests you have in the comment section so they can be added to future videos. Thank you.